discussing a presentation about neuromorphic compute. Professor Panda from Yale University, she has been working on neuromorphic compute since her PhD at Purdue for probably about at least 10 years now. Interesting field because it looks at information processing from a different perspective. Fundamentally, what neuromorphic compute means is that you look at, for example, an image not in terms of relationships between pixels, but in terms of how they spike. I'm going to explain what that means in a second. So it's a temporal model, and it attempts to mimic how the human brain works, and therefore has the potential to save a lot of energy and make computation and learning a lot more energy efficient. This is not even on podcast. It's February 3rd, 2025. This is Krimdelko for the data fund is down 5.2%. The market is down 1%. For the year, we are down 7.5%. The market is up 2%. We're underperforming by 9.5%. So Professor Panda is in the field of neuromorphic compute. Really interesting presentation today at the Stanford hardware department, so computer engineering hardware. I think this is a field that we've discussed several times. We have a large position in NVIDIA, obviously. We're very interested in this field, and I think we want to come at this field from three different angles. So I guess the first conversation is about, what is this all about? What is neuromorphic compute actually trying to achieve? Second, how are existing methods, in particular, GPUs and the NVIDIA platform, mitigating some of these? And then third, maybe a little bit of an outlook of post-von Neumann compute architecture, of a domain-specific architecture. We spoke about this last week, things along those lines. So let's start with what is actually neuromorphic compute. The idea is that you look at the world from a spike perspective. So let's say, for example, a cat is not defined by its relationships of pixels, but by the way neurons spike when signals come in. And a car and a tree and a palm tree and a red car and a blue car, and all of these things have their unique signature in what's called time domain specific neuromorphic structure. Now, I apologize for all these words. There's a handful of words that probably don't make a lot of sense to people, but just think about this very, very simply. Instead of defining a cat, like we humans, when we look at, for example, a cat, we look at an image of a cat, and the way a computer might be looking at a cat is actually by the way neurons spike in a time domain, so from one time epoch to the next. That's the fundamental idea. So this is sort of a mixture of analog and digital compute, and the big advantage is that if you do it that way, you really only process information that is necessary to define a cat. You don't have nothing else spikes, just whatever the cat is supposed to be represented with, or the car, or whatever. And I think this, to us, is really interesting because it could have big applications, particularly in robotics, because as Panda et al. Mentioned in their seminal Nature paper that was published in 2019, one of the drawbacks of neuromorphic compute is actually the lack of data, because most of data that we know is static data. It's like Wikipedia and images and ImageNet and things like that. So we don't have actually a lot of four-dimensional data. And of course, in robotics, it's all about four-dimensional data, the 3 dimensions plus time. And therefore, that could be actually not just a good way to train neuromorphic compute, but it could be the way to train neuromorphic compute is actually through robotics. So we believe that it wasn't really mentioned in the presentation, but we believe that this type of approach has a lot of potential in robotics. And that brings us to the next point, which is, okay, what do we have right now, and what could be, how could we mitigate some of the drawbacks? So the biggest drawbacks are there's 2 fundamental drawbacks in training. It's energy consumption, as defined by the data transfer. So it's the memory wall. I think we've spoken about this a lot. We call it the neuromoprhic effect just because he was the first that made us pay attention to this. And mitigation techniques are you try to keep the data close to where the compute is. You try to compute in memory. You try to move as little data as possible back and forth. Flash attention, actually, Professor Panda mentioned flash attention is the attempt to sort of compress the necessary computation, the necessary data for computation onto a CUDA kernel. In other words, you want to have all the data necessary in one shot for computation, so you don't have to move data back and forth, which solves the problem with the memory wall. So in general, I think what we have right now in the training side of things is a highly optimized network of GPUs and software platforms on top of them. Blackwell, the latest one from NVIDIA, to save energy and speed and money. We said several times that the name of the game is dollars per token or watts per token or tokens per watt. You either minimize or maximize depending on which side of the equation you're looking at. And this neuromorphic compute is a new way of thinking about compute. Again, it's an analog and digital amorphous thing. So it's both, and then you define an object by the way it spikes neurons. This requires new types of algorithms. This requires new types of hardware, and I think people like Professor Panda are working on this, and it's very exciting. And I think it shows that science and technology can actually really work together towards really revolutionary new ideas. Now, the question, of course, is, and this is sort of the third thing we want to talk about a little bit, is the perspective here. So where do we stand? But how can this actually turn into something real? And I think actually robotics could be the killer app for this, because robotics deals exactly with the time dimension. And Panda talks a lot about time. Time is the key here. Okay, whenever signals come in, the timing of the signal is actually what defines the object. So as opposed to some sort of relationship between pixels that define a certain feature set and then define the object. In this case, it's the time, it's the relationship between when the signals come in, which defines what an object is. And I think that in itself, it's a new way of thinking about compute, and it's also a new way of thinking about, in general, about intelligence. So intelligence is the sort of temporal relationship between neural spikes. So to summarize this presentation, I think it was inspiring. It's a interesting field. It's a nascent field. We've seen it before in different other fields. Maybe I should mention also a couple of things that Panda also spoke about, like quantization, pruning, things along those lines that NVIDIA is doing also, right? I mean, I guess we could think about, in general, we could think about the idea of machine learning as a general purpose compute paradigm as, okay, it's a signal processing problem where you're trying to extract intelligence, not just reproduce information. So it's not signal processing 101 where you send a message and you want to encrypt and decrypt the message with high fidelity. What you're trying to do is you're trying to learn things. You're trying to extract knowledge from a set of input of data, and you could do that with signal processing techniques, or use neuromorphic compute as a paradigm for that. And that would require different algorithms and different hardware. But the fundamental idea, again, is that you define the unit of analysis is the timing of neuron spikes, as opposed to relationships like, let's say, the relationships in the transformers, which are sort of attention of tokens to each other. Here it's the temporal relationship between spikes. Thank you.